All right. Good afternoon, everybody. And for those of you on the West Coast, it's still morning, so good morning. Welcome to the first webinar in a series of five addressing reduced data set. I'll mention a few things at the beginning here. At the bottom of the left-hand side, you can actually download a PDF of the presentation. Also in the chat pod, you'll be able to ask questions. In the note pod, we provided information on the ADT reduced data set and also provided information on the series of the five webinars and approximate dates in terms of the months. We will provide the exact date and send an invite to everybody who attended today's seminar and also through the distribution list when we get close to those dates. To begin, I would like to give Yusuf Muhammad Shah with Federal Highway Administration and Turner Fairbank and the STAC a chance to welcome all of you and briefly introduce the seminar. Yusuf?
Thanks, Omar. Good morning or good afternoon, as the case may be. Thank you very much for attending today's webinar. This webinar is part of a project with VHB and CITRI to support the Federal Highways STAC in utilizing the SHARP2 Roadway Information Database. I want to thank Omar and his team from Center for Transportation Research and Education at Iowa State University in putting together this seminar and developing the reduced datasets. As Omar mentioned, my name is Yusuf Muhammad Shah with Federal Highway Safety R&D. I am the manager of RID Technical Support Task Order, and this is first of 5 webinars that CITRI will be conducting to introduce Federal Highways effort to support safety and other research utilizing the SHARP2 safety data. We have previously developed other reduced data sets in a separate project. The 5 reduced data sets which were developed before were curve data set, lane, divided versus undivided highways, intersections, and speed limit. These data sets are available once a copy of RID is purchased from CITRI. In this webinar series, the 5 reduced data sets that will be developed are AADT, which is this current webinar is going to be intersection width, intersection crashes, curve crashes, and homogeneous segments. We will send you the dates for these webinars as and when they are finalized. With that, welcome everyone, and I will hand over to Omar to continue the webinar.
Thank you, Yusuf, and I do definitely want to extend our thanks to Federal Highway for funding this work and also for VHB, who is the prime contractor. C3 is a sub to VHB on this project. Before we actually get started, I have a couple of poll questions that I want you guys to look at. The first one is basically going to be your organization that you're representing today. So I'll give you a few seconds here. I see people are already responding in terms of the organization. We have several folks from Federal Highway. We have we have 5 from state DOTs. We have 7 consultants and 8 academia. I'll give you 5 more seconds, and then I will close this poll, and I can broadcast the results so you guys are able to see it. I think we have good numbers, so I'm gonna end this poll. My second poll is going to be on how many folks actually you have with you watching this webinar so we can get a good idea about the attendance. So go ahead and fill those out. I'll give you 10-15 seconds to answer the poll question. We have some majority are singles, and we have a couple that are 2 and 3 at this point. So I'll give 5 more minutes for everybody else to 5 seconds. Yes, thanks, Skylar. And while you guys are answering that, I'll also introduce Skylar. Skylar is going to be doing the majority of the webinar this afternoon. He developed the reduced data set in support with also Zach Hans. I'll be doing a little bit of the introduction, and then Skylar will address the technical details in terms of the ADT reduce data set. I do have another poll at the end of the webinar. So while you're listening, also keep thinking about additional reduced data sets that you might be interested in as a state DOT or as a researcher working with the Roadway Information Database and the naturalistic driving study data as we go along. So I will make sure that we will save time at the end of the webinar to give you a couple of minutes to provide us input on additional reduced data sets that you would be interested in. All right, let's go ahead and get started. So our webinar today will basically talk a little bit about how we selected these reduced data sets. And then specifically, we're going to be talking about the average annual daily traffic data set in terms of the description of the data, the benefits, the methodology that we followed to develop the data, the attributes that we have in that data set, how can you use it, and then importantly also the assumptions and limitations that we made and we faced in terms of developing the data. And finally, we will chat a little bit about how can you link that data with the NDS data. So now you have roadway data and also you have vehicle and driver data. Yusuf touched on this a little bit when he did the introductions. We actually have 6 reduced data sets so far. One was developed through our work with TRB on speed limits, where we were able to develop a speed. Well, speed limit was federal highway. Sorry, okay. Skylar is correcting me. Speed limit was federal highway, and TRB was the mobile HPMS presence reduced data set that is at the bottom here of where I have my pointer. Those are already available as part of the RID. So if you're getting a new copy of the RID or if we sent an update to existing users, it would come with these 6 reduced data sets. So to be able to identify additional reduced data sets, we did a survey of the RID users and researchers, and we developed a white paper for Federal Highway on those reduced data sets. And you can see on the right is just the ranking from for the different data sets. You can see a list of these data sets here on the left-hand side. Those are ranked in terms of the priority that the users felt were important to them. So roadway attributes for crashes had the highest priority. Comprehensive work zone data set had the lowest priority. So we started with 9. We also provided the users of the takers of the survey the opportunity to actually give us some ideas in terms of additional reduced data sets that they want. And we ended up, I think, total with 12 reduced data sets that were feasible. And we developed a white paper that talks about the effort to produce them in terms of time and cost, the feasibility, what some assumptions might be, and also what are potential uses of these reduced data sets. Federal Highway, through this project, selected 5 reduced data sets to develop based on, as I said, the ranking, the feasibility, and also the cost. Yusuf mentioned those, but here's just a summary of them. We're talking about the AADT reduced data set that is complete. That's what the webinar is going to be on today. We're planning on finishing one intersection widths by November this year, and then one that summarizes crash data for intersections early next year, and then the curve crash summary in March, and the homogeneous segments one in May. There are others that Federal Highway is considering, and I think we already have a mod to the contract to develop 5 more. We haven't agreed yet on what those five are, but there will be additional data sets that will be developed as part of this work and support the STAC, the state DOTs, and researchers in terms of how to use the roadway information. The deliverables for each one of those reduced data sets would be a webinar on each one like we're having today, step-by-step documentation in terms of how we developed it, a user guide, and then this becomes part of an update that we will issue to the RID. So any user that currently has access to the RID will be able to get these additional reduced data set. Here is at the bottom here, there is a link to the RID website where you can get additional information about the webinars and also background information and a sample data set that you can download from the website, the RID website. With that, I'm going to turn it to Skylar and have him start talking about the technical details of developing the AADT reduced data sets.
Yep. So whenever we started the white paper that Omar discussed, some of the feedback we got was that users wanted an easily accessible AADT data set. They wanted something that was consistent across all of the 6 states and was something that's uniform in a single layer and has all of the data combined. So really our objective whenever we started out creating this reduced data set was trying to meet these goals of having something that's easily accessible, consistent across the states, and users know exactly where it is and how they can use it no matter which state is they're doing their evaluations in. So it's been a highly requested attribute. We consistently get questions from researchers about how they can access the AADT, and the often difficult part whenever we're responding to them is that there's multiple layers within the RID that contain the AADT. There's typically a layer that has that information, but then it's also contained within the HPMS data within the RID. There's also some other layers that is more business data that has the AADT information in it, as well as we were collecting data for multiple years within the RID. So you could have AADT data from 2010 to 2013, which are all consistent in each layer. In addition to that, the layers weren't always consistent. So the coverage for one layer may be for only state roadways versus the coverage for a different layer may contain all roadways. So the users really had to investigate which layer they wanted to use, and if they wanted to use multiple, it required a little extra effort on their end to integrate the data so that they had the most accurate information. In addition to that, most of the DOTs provide the AADT information for only a single center line, and with the RID having divided center lines for some of the roadways, this often left data only conflated to a single direction. So whenever you're using the RID and doing any sort of dynamic segmentation, you may not get any AADT return because the data was only conflated in the single direction, which could be the opposite direction of what you are evaluating. So the benefits that this AADT reduced data set tried to achieve was having a unified traffic data across all the states. So having a consistent layer that is always present in all the layers, that is the same name and has the same contents available, whether you're looking at Florida or whether you're looking at Washington. We also wanted to try to set out to have the data available on both directions of roadway. Users have the perception or have the expectation that wherever they do their dynamic segmentations or are using the RID, they expect that AADT to be there. So we wanted to get away from the extra effort that users would have to do of identifying the divided roadways and then trying to identify where AADT exists and where it doesn't exist. And then the last benefit that we wanted to have was we wanted to have all the data for multiple years on a single segment of roadway. So at each location, there's only one record that contains the data for multiple years so that the user isn't having to dig through multiple layers and multiple years of data to find out what the AADT is across the multiple years. So to create this, we broke our methodology down into 4 steps. The first step was identifying which layers within the RID actually contained AADT information. So this involved opening up all the layers and figuring out which ones actually had the traffic data as part of it that we could use to build the reduced data set. Our second step was reconflating the data. So this was our process to try to account for the single center lines that the data was typically delivered in, and providing the AADT on both sides of the roadway on these divided roadways. Then our third step was identifying any ambiguity and duplicate data. There are some issues whenever the data was originally conflated to the RID, which causes some ambiguity where multiple AADT values are reported for the same segment of roadway. So we wanted to identify those so that, one, it reduced the number of records that are within our reduced data set, but then it also just notifies the user that there may be some ambiguity here, and that these locations may need to be further explored, in helping the user in identifying those locations. And then finally, the reduced data set was created, which is merging the multiple years of traffic together, as well as integrating the HPMS data. So we had a consistent, unified AADT reduced data set for all years in all states. Whenever we were creating the reduced data set, everything was done within ArcGIS and Excel. So there was no additional scripts that we were using. We tried to do this so that even basic users would be able to create this reduced data set, as well as seeing what techniques we were using to integrate the data that could be applied to different situations or different applications that researchers want to do. In addition to this, we had a step-by-step documentation, so it actually details every single step that we use to create the reduced data set for a novice GIS user to be able to recreate the data set if they wish. That also, again, has some tips and tricks that we use along the way to create the reduced data set that may be beneficial for other users to apply to a different situation whenever using the RID. And then finally, we have a user guide, which again gets delivered along with the RID, which will cover a lot of the things that we talk about today, including the methodology of how the RID was created, some of the limitations and assumptions that were made when creating the reduced data set, and then the benefits and just a high-level description of what the reduced data set is. So starting off with our first task in creating the reduced data set was identifying the layers with traffic data. So we, like I said, we opened up every layer within the RID and tried to identify whether there was any traffic information in any of the fields within each of the layers. Once we had those layers identified, we then tried to figure out whether they were point locations or whether they were continuous features or linear segments that we could use in the reduced data set. We made the decision to remove any of the point counts or short-term counts since they would just be point locations, and we were looking for more coverage across the entire state. So we ended up reducing it down. Below on the right is some examples of the summaries that we did, and you can see the layers in bold were the ones that we ultimately used within the reduced data set, and we ultimately decided to go with the tops layer for HPMS instead of the sections, since it was continuous and everything was aggregated together instead of the sections, which maintains everything independently. From there, we got into the reconflating of the data. So whenever I say reconflating, what I'm talking about is bringing the data from one side of the roadway and reconflating it to the opposite side of the roadway. So in this image here on the right, the green line represents the original data that we conflated that's located in the RID. But because this is a divided centerline roadway, the data for the opposite direction, in the original data, we had no data there. So what we were trying to accomplish during the reconflation is bring this data from the one side of the roadway and represent it on the other side of the roadway, so that whenever you're doing dynamic segmentation, you always have data available, and it can be you'll return some AADT information on that segment of roadway. To do this, we use the routes layer, which is the base layer when everything is represented on in the RID. Within the routes, there's a field called route name that has a fairly consistent structure, which is represented here at the bottom with the numbers and the pipes, and then the route name and the direction. With this, we were able to identify whether it was a divided roadway based on the last digit in the route name. If it contained a letter, either N, E, S, or W, we knew that those were divided roadways. And if it included a 0 or a 1, then those were undivided roadways. And then the route name was used for checks on our end to verify that it was reconflating to the right direction of roadway. So first identify the divided roadways. Once we identified all the divided roadways, we started splitting the data into the north and east routes and the south and west routes. This was one of the assumptions that we had to make along the way, that we would identify the data that was in the south and west direction, and then we would attempt to reconflate that to the routes in the north and east direction. So that gets us the reconflating to the opposite direction of travel and forcing it to go to that opposite direction of travel. So you can see that we use the locate features along route, which is a part of the ArcGIS toolbox. And in this case, we took the AADT 2010 south and west data, and we conflated it to the routes in the north and east direction. So reconflating it to that opposite direction so that it would be represented on the other side of the roadway. Since we had to do this for both directions of travel, we then merged those two files together to create a single feature that included both of the reconflated directions of travel. And then we started implementing some of our quality checks. So the first one that we did was the route name had to be the same. So if the data was on Interstate 81, it had to be conflated to the Interstate 81 in the opposite direction of travel. We didn't want it to reconflate to any side roads or any other divided roadways along the area. So that was one of the limitations that we developed within the system, was to make sure that it was on the same route based on that route name within the identifier. And then we also did a direction check to ensure that we weren't being conflated to the same direction of roadway or the same direction of travel, even though the system should, based on how we did it, conflate it to the opposite direction of travel. And once that was completed, we only kept the records that met both of the quality checks, and we used that to add to the merged data. But the one other additional assumption that we used was that the original data that was conflated to the roadway was the most accurate information, and if we reconflated data to the same roadway, we used the original data over the reconflated data. So we used dynamic segmentation to identify those locations which already had original data, and deleted the reconflated data because the original data was already present. Once that was completed, we merged those two files, the original file with the reconflated data together, and create a more unified layer which has the AADT for both directions of travel. This process was completed for all layers which were identified as being included in the AADT reduced data set. So this process had to be ran multiple times for each of the layers. Once we had those layers created and our base data that we wanted to use as part of the reduced data set, we wanted to identify if there was any ambiguity in each of these layers as well. So whenever I say ambiguity, it means that we've got multiple values or multiple AADT values represented for the same segment of roadway, but the values are not the same. So we could have a one value that says the AADT is 1,000 and another value that says the AADT is 22,000. We don't have a system in place to identify or validate which value was correct. So we wanted to identify those locations to bring it to the user's attention that there is some discrepancy in what the AADT value is on this roadway. And then duplicate data is identifying sections of roadway that have the exact same AADT value, but are just duplicating or causing duplicate records, which we wanted to eliminate so that there was only a single record for each roadway. To do this, we first identified all the change points, so anytime there was a break in any of the segments for any of the data located within the layer, so that we knew where we were seeing changes in the AADT across the entire network. With all those change points identified, we were then able to create a base layer, which is a unique section for all of the routes across the entire network. And with that base layer, we were then able to perform dynamic segmentation with the original data to identify how many records were present on each of the unique segments across the network. So whenever we do the dynamic segmentation, you see that there's only one record at this location, but then in other locations where we have overlaps, we have two records present, and this would be our indicator that there may be some ambiguity or there may be some duplicate records at this location. To give a visual description of the duplicate data and the ambiguity, we just put some numbers here. So for this data, this original data, an example is we've got 2200 AADT for this section, where this other straggling segment, we have the same 2200 AADT. For the location that we are overlapping here, we would identify this data as duplicate. In these situations, we would remove one of the duplicate data so that we only have a single record available at this location, and we're not creating extra segments that aren't necessary. Another example is ambiguity. So in this case, for this same section of roadway, there was a 2200 AADT reported, but there was also 2500 AADT reported. We would identify these sections as having some ambiguity since we don't know which value is correct, whether it's a 22 or 2500, and we would flag these records as having ambiguity for the future use of that data when creating the AADT reduced data set. So at this point, we would then summarize the data for final integration. So this whole process was created again for each of the layers of identifying the ambiguity and duplicate data. We would reduce all of the other fields in each of the layers to only include or only retain the AADT and the truck percentages. With the flag data that we identified as ambiguous, we would summarize that data and provide the minimum and maximum reported values. This was a decision that was made to keep the data clean and keep it in a fairly consistent manner, because in some cases we were seeing up to 5 different AADT values reported. So we wanted to just report the minimum and maximum value, so it gives an indicator to the user that there is some ambiguity and they want to further explore it, but then also providing the minimum maximum value so that they could compare it to the other features.
And here, this is data that we are utilizing that we did not collect, we did not do any quality assurance on. This is data that was provided by state DOT or through HPMS. So we wanted to provide the users with as much information as possible and also as much guidance as possible. So in this case, where we don't know which one is more accurate, we provided this range, and we also said, this is ambiguous. We don't know which one, but as a user now you can understand that the segments might have erroneous data, and you will find also the range for that erroneous data. Do you have enough segments that have good data to do analysis? Definitely. There's a lot more segments that are less ambiguous or no ambiguity there in the data than there are segments with ambiguous data. But we did not want to delete data. We did not want to clean that data, by taking averages or things like that. We just wanted to provide the users with guidance in terms of what we have as AADT data, and then give you as a user the chance to decide what you want to do with it.
So we then get into the final step of creating the reduced data set. So at this point, we've reconflated the data for each layer, and then we've now summarized the data for each layer. And now we want to bring all of those layers together to create a single unified reduced data set that has consistent form and structure for all of the states. But to do this, we could potentially have multiple years of data or multiple layers representing the same year. In addition, we also have the HPMS data, and we wanted to put that as a lower priority since we had more confidence in what the state was providing. Since the HPMS data is actually provided by the state, we wanted to rely on their data first from the state. So we first looked at all the different layers. In this example, we're looking at North Carolina, and we had 4 different layers that were provided by the state, which include the roadway inventory, the AADT 2010, AADT 2011, and AADT 2012. The tops layer is our HPMS data, so we wanted to first evaluate these 4 layers to prioritize and rank those for each year. For 2011 and 2012, there was no other traffic data available, so those would be our layers that would represent 2011 and 2012 for the AADT reduced data set. Whenever further exploring the roadway inventory data, we actually identified that that was 2010 AADT data. So we knew that we had 2 different data sets from the state that both contained 2010 AADT information, and we had to make a decision on which one of these to use. To do this, we first wanted to prioritize data that was had a purpose of traffic data, since the sole purpose of the layer was only for traffic. But then we also wanted to look at the uniformity with other layers. So in this case, the AADT 2010 was prioritized since that only contained the traffic data and it was consistent with the 2011-2012 data. The roadway inventory also had some other business roadway features such as the surface condition, the pavement condition, the surface type, the jurisdictions, the road class. So the priority of this, or the purpose of this feature, wasn't solely for traffic data. So we wanted to have that as a lower priority and only use that to fill in the gaps.
Scholar, there is a question from Charles Fay. He said, do you let the users know where the data comes from if more than one value is available?
Yep. So right now, the way we've got it is we just have it broken down by either state or HPMS. So there is a source field in there that lets you know what the source is, whether it's AADT or whether it's a state-provided data, or whether it is the HPMS provided data. We don't provide a distinction within the years. So in case of 2010, we didn't provide a distinction of whether it came from the roadway inventory or whether it came from the AADT 2010, but we did note that it did come from the state. So once we prioritized the layers, we wanted to fill in the gaps with the lower priority roadways. So in this case, on the map, all of the red lines represent the highest priority roadways. So in our case here, it would be that AADT 2010 layer, and then all the locations in green are where there was no data from that highest priority layer, but there was data at the lower priority level. This could be due to issues in the conflation process for the higher priority level, but for whatever reason, there just wasn't any data at that higher priority layer. But we didn't want to just leave the gaps there, so we made the decision to fill in those locations with the lower priority data, so we had consistencies throughout the process. So, and to do this, we use dynamic segmentation to identify those gaps, and then essentially only retain the locations in the lower priority layer where there was no other data from the higher priority layer. Once that was completed, we then had a layer for each year of the state data. To integrate all those together, we performed dynamic segmentation between all the state data for all years. This ends up creating the single layer for each of the for all the layers. So in this case, for each line in this data, we have a section that has just the 2010 data, and then another section that has the 2011 data. So each record has all the data or all the years of available AADT data that was present within the RID. Our last step was then to integrate the HPMS data. Similar to how we did the highest priority and the lowest priority, we only wanted to use HPMS data when there was no other AADT data available for that specific roadway. So we did a similar process of using dynamic segmentation to identify where there were gaps in the reduced data set and fill in the HPMS data at those locations where there was no other AADT reported. So again, deleted or only retained the locations without AADT with the HPMS data but no other AADT reported, and merge that with the final reduced data set to create our final reduced data set. The output ends up creating a single or AADT data for the entire network across the state. It contains all the years of relevant data that we'd identified, as well as identifies any ambiguity that we had identified throughout our process. So it's a single output layer. Each roadway will only contain one record, which contains all the data that we were able to identify through our process. It makes it easy for the user to understand and correlates with their expectations of how they expect to use the RID whenever doing dynamic segmentation or any other analysis. For the attributes that we retained, for each year of data, we have 5 separate attributes. The first 2 attributes are the AADT values with the corresponding year denoted, and then the AADT with the corresponding year and the underscore alt. If there's only a single AADT value reported, this AADT alt will be a null value, but if there is ambiguity identified in this location, we will put the maximum AADT reported in the AADT 2010, and then we'll put the minimum value in the AADT 2010 underscore alt. This helped clean up the reduced data set so we didn't have 5 or 6 different fields with all the different potential ambiguous AADT values, and just made it simple to use for the users, knowing that there's only 2 fields and that the AADT 2010 underscore alt is only relevant whenever there is ambiguity. And then the same application applied for the truck percentage with the underscore alt layer. And then getting back to Charles's question, the source layer identifies what the data source was for that given year, and it will either be the state data or from HPMS. Here's an example of the actual reduced data set. So in this case, in ArcGIS, I've selected a single segment located along the roadway, and then the attributes for that segment is located here along the right. You can see we still have our route ID and from and to measure, so that we know where that segment is located along or within the RID. But then we have each of the 5 layers that we talked about. So for 2010, you have those 5 layers. The same thing for 2011, 2012, and 2013. In this case, we had no ambiguity. So for 2010, we had a reported value of 61,000 for the AADT, and it was provided by the state. We didn't have any truck percentages reported from the data that they provided. In 2011, we had an AADT of 59,000. Again, no ambiguity, so the alt field is null, but we did have a truck percentage reported, and this was provided by the state. And then the similar information for 2012 and 2013.
And as you can see on the top, this is from North Carolina.
Yep.
So the organization of the RID is still the same in terms of a layer for each state.
Yep. Here's an example of what we would experience whenever we do have ambiguity. In this situation, I've again selected a segment within the RID that is reporting the AADT from the reduced data set. In this situation, there's likely a conflation issue due to the side road being located here, and some of the original data that we received from the state being incorrectly conflated to the main line. So in these cases, in 2010, we had ambiguity where there was a report of 35,000 AADT as a maximum value, and then there was also a reported value of 10,000 AADT for this section of roadway. With that, there's that ambiguity. And since we don't have the capability of identifying which one's correct, we just report that minimum and maximum value. You see that same thing in 2011 with a 33,000 AADT and a 9,700 AADT, and the same thing in 2012 with a 40,000 and a 9,800 value AADT. In this situation, there actually wasn't any ambiguity in 2013. So you actually just have a single reported value of 37,000, and that's where it's you have the benefit of having multiple years of AADT available in a single layer, because you can actually cross-reference these together. And most likely in this situation, the maximum value AADT is probably the correct AADT, since it correlates well with the one AADT value that didn't have any ambiguity at this location. So using the reduced data set, it's just like any other layer that's located within the RID, specifically like the mobile data, where we have coverage on all of the roadways. You have the expectation that there's data available on those roadways, whether it's a divided or undivided roadway. The coverage is fairly comprehensive across the state on all the major roadways. We can use the layer, whether it's for dynamic segmentation or spatial selection. So it would be similar to how you would use any of the other layers within the RID. We anticipate using this for a lot of safety analysis. That's where most of our requests have come in so far, of wanting to bring in the AADT value to see how much traffic is on these roadways where they're evaluating the safety performance, to be able to do crash rates or anything else, or prioritizing locations for their analysis. In addition, if you're specifically looking for high volume locations, you can prioritize your data requests to only have the AADT above a specific threshold. Or if you're looking for low volume roadways, you can do the same thing of identifying those locations with lower volumes. Getting into some of the assumptions and limitations that we have within the RID, I've kind of mentioned some of them along the way, but kind of digging into the specific assumptions that we're making. One was that we divided the data by north and east and south and west, and made the assumption that if the original data was for the northbound direction, that the opposite direction of travel would be south. So the major assumption is that those directions would be opposing. We're relying on the data that's available within the RID, so this is probably going to be consistent across most of the roadways, but if there is a situation where one direction is reported north and the opposite direction for some reason is reported as east, we wouldn't conflate the data to the opposite direction of travel, and the data would just be available on that single center line if it was occurring that way.
Skylar, I'm going to stop you since we have a question on I think this slide, or maybe this one. So the question is from Dan Cook. It says the ADT that was shown on the divided roadway in the previous example, is it for just that direction or for both directions combined?
So we're using the data that was provided directly from the state. In most situations, it's a single center line, so it would be the AADT for both directions of travel and not for a single direction.
And from Maricopa Association of Governments, what were the conditions used for dynamic segmentation? Do you have enough to answer that question? Details?
So we use dynamic segmentation in a lot of the different steps throughout here. In most situations, we were using the union dynamic segmentation, because we wanted to identify locations with or without the data, and that was what we were using primarily whenever we had the highest priority or the lowest priority roadway. Whenever we were getting into the final actual reduced data set, those were actually using the intersect dynamic segmentation, because we wanted to retain all data, whether there was data available in the other layer or not.
And this whole thing is based on the premise that we have a linear referencing system. So all these data sets have the from measure and to measure, which basically relates that to a linear feature on the road. So the ability to do that dynamic segmentation, whether it's union, intersection, or overlay, it's basically based on the idea that we know the location of each one of those features, and then we're able to run that dynamic segmentation to basically summarize data that have different representations graphically, linearly, or location-wise.
And actually, I stated that wrong at the end. We did use union dynamic segmentation for the final integration as well because, again, we wanted to use all the data, whether there was data available or not. So actually, we used, I think, union for a majority of the steps that we produced. And then we were using all the functions within ArcGIS, so the toolboxes that they have there of overlay and route events within the ArcGIS.
Hopefully that answered your question. If not, please provide us a little bit more detail.
So whenever we were doing the reconflation, we took a really conservative approach because we didn't want to misrepresent or displaying the data for a roadway that it wasn't actually reported on. So one of the ways that we did our approach was we made the requirement that the route name did match. So in our example below, if the original data was on Interstate 81, the reconflated data also had to be on Interstate 81, and the only difference that we wanted to see was that the direction of travel had changed. And as you can see in the image, for most of the situations, that's the case. Where we're seeing the green is the reconflated data and our red is our original data. Along the left side here, you can see a lot of that original data didn't get conflated to the opposite direction of travel where there was a roadway. This was due to one of the directions of travel on the divided roadway being reported as a state roadway, and then the other direction of travel being reported as a U.S. route. So since those route names didn't match, we didn't conflate the data to the opposite direction of travel because we had that requirement that the route names must match.
And the good thing here is you have so much data that it is better to be conservative rather than get into issues where we might have errors. So we wanted to be consistent, and because we knew that we would have a lot of ADT data, a lot of segments that have data, being conservative was really the best choice for us to take.
Yep. And so limitations of our conservative approach is we may eliminate some of the reconflated data that is correct. So for example, here on the image to the left, this data likely was, the red is our original data again. It likely was reconflated to those sections where we're seeing gaps in the reconflated data. But for some reason, the route names, or because we were at this intersection, there was some issues that we were seeing that we didn't end up including that data. So we're eliminating some of those locations, but we're minimizing the potential for errors of data getting conflated to an incorrect roadway and saying that a roadway has a higher volume than what it actually is what it actually is. The other limitation that we did was we used 150-foot radius. So we only would reconflate the data if there was another divided roadway within 150 feet. We did a sensitivity analysis of looking at anywhere from 50 feet to 500 feet to see how the reconflation process performed. Once we started getting up into the higher distances, we started seeing a lot more errors in what was being reconflated in terms of what roadways they were being reconflated to, as well as the start and end locations of where the data was being reconflated to. So ultimately, we decided to go with 150 feet and use that throughout the process, even though we know some of these divided roadways may be separated by more than 150 feet.
So question here from Kiri Hancock is no data entered as null or zero?
So if there's no data available, it wouldn't show up in the reduced data set. In these situations that we're talking about here, we're mainly focused on just the divided roadways. So there would be no data represented on the opposite direction of travel if it wasn't reconflated.
So if it's zero, there's really no zero ADT.
Yeah,
It's either
there would
it's
be no
none.
zero ADT reported in the reduced data set because what we there may potentially be data available in other years, so we didn't want to say that there was a zero and potentially uh, miss out on data that was available for those other years. Uh, So overall, we felt very comfortable with our reconflation process. It was able to handle a lot of complex situations. As I mentioned, we did, since most of the data from the states was a single center line on our divided roadways, they would only conflate to the closest direction of travel. So in this situation here in the top left, the red is our original data. So we had situations where the single center line was closer to one side of the divided roadway, but then for some reason end up switching to the other side of our divided roadway. Our process was able to handle that accurately and reconflate the data, which is represented as green, to the opposite side of the roadway. So we had all AADT values represented on all roadways. In addition, we have a lot of sections within the RID that switch between a single center line to a dual center line or a divided roadway throughout the route. In this situation, you can see it changes from a single center line to a divided roadway, back to a single, and then back to a divided roadway. We were able to reconflate that data to the opposite direction of travel in these situations so that we had AADT reported on both sides of the roadway.
Charles has a question in terms of, percent of the data set with no data. And for those segments with no data, any guidance provided to users if they wanted to determine on their own. I mean, the RID for the 6 states represents a huge mileage. So we only had ADT available from state and also, which basically from state roads and also HPMS, which will have sample segments on roads other than the state DOT. So I would say probably, I mean, we have not done that, but the percentage would be probably less where we have ADT data would be less where we don't have ADT data because of the vast majority of the local roads that are part of the RID, especially within the study areas. So in terms of guidance to users, I mean, if you don't have what you need in terms of the data and you're focusing on a specific geographic area, you gotta basically go back to the local agency or to the DOT to see if some of that data exists, which is not an easy task. So our suggestion would be, find locations where you have the data. Otherwise, it's going to get a little bit more complicated.
One of the other assumptions that we made was that the data that was originally conflated to the center line is the correct data or is the most accurate data for that roadway. So whenever we did our reconflation process, some data would get reconflated to roadways that already had original data located on those. So whenever we did have that situation, we would disregard the reconflated data and only use the original data that was present. In this example on the right, what we had was an interstate, and we've got ramps that come along this roadway, and this part of the road is technically labeled an interstate in our routes, so they were classified it as divided roadways, and some of the data got reconflated to this route during our process since it was technically considered a divided roadway. But since there was already original data on this roadway, we would disregard that reconflated data that's represented in green below the red line. So overall, we were really comfortable with our process. We had a significant expansion in our coverage of the AADT. This is just a map that shows you again red where we have AADT reported, and then original data reported, and then the green is our extended coverage that we were able to capture due to the reconflation. And you can see most of these are on those divided roadways, and we were able to report the AADT on both sides of the roadway. We feel like this aligns better with the user's expectations that all roadways, whether they're divided or undivided, should have an AADT value present on them, and that they don't have to run into the issue of not knowing whether there's any AADT value there or whether they need to figure out some other process on divided roadways to identify what the AADT data was for the opposite direction of travel. Ambiguity, as I mentioned earlier, is often due to some incorrections in our conflation process. So for some reason, it got conflated to the wrong side of the road, or it got conflated to a side road, even though it was supposed to be on the main line. We don't have much control or ability to really identify and correct all of these issues. So the assumption that we made was that we would just report the maximum and minimum values whenever we identified that there was any ambiguity. In some locations, we were able to see that there were up to 5 values reported. We debated including all the values that were reported as part of the when we were identifying any ambiguity, but we determined that would make the reduced data set too complex, and we figured that the minimum and maximum values were sufficient enough to identify that there was some issues in that location in getting the correct AADT value, and that would be sufficient enough for a user to further explore or further identify that they need to do some more evaluation at those locations. These represent only a small fraction of the data. I don't have an exact number, but overall it's a very low number of roadways that have ambiguity compared to the total miles of roadway that we have present. Another assumption that we had was the prioritization of the data based on the purpose. So as I mentioned earlier, whenever we had multiple state data available for a given year, we would prioritize any data that was developed primarily for traffic. We were not limited to segmentation defined by other roadway features or summaries of AADT based on other features. And this gave us longer segments, and we felt it was more accurate than any other business data that was just reporting the AADT as kind of an additional attribute within the layer. So similar again to all the other layers in the RID, to link with the NDS, we use our link IDs contained in the links layer to request data from VTTI. You can use dynamic segmentation between the AADT reduced dataset with the links layer in the RID to identify those locations that you're interested in, to get the link ID that you would then send to VTTI. Or you could do some other process of integrating other data sources, but again, the links layer and the link IDs are our main communication component between the RID and the NDS. And finally, integration within the RID. Once the reduced data set is approved, we will begin the integration process so that all future deliveries have this AADT reduced data set, similar to how we've done this for all of the other reduced data sets to date. There will be a single layer within each data warehouse that will have that consistent name of AADT reduced data set, which is shown here in that top image. So the name will be consistent across all of the 6 study sites. In addition, we have a documentation folder within the RID. This includes the guides that we've produced for all of the reduced data sets to date. And this will also include the step-by-step instructions of how the AADT reduced data set was created. So you'll have that documentation, and a lot of the content that we've talked about today will be located within that user guide. In addition, we also update the data summary file and the metadata file that are located within the documentation, which summarizes all the fields that are available within the reduced data set, as well as what information is available within those, and a description of those fields within the reduced data set.
All right. Thank you, Skylar, very much. Here is my email if you have any questions. So what I want to do right now is I'm going to open the floor for questions. I know we've been answering some as we went along, but I also want to make sure that you have the opportunity to type in what you think you might need in terms of additional reduced data sets. We will share those with Federal Highway and see you know if whether they're feasible or not. So I'm gonna leave this on. I'm not gonna end this until we're completely done with the webinar. I also want to mention that you know the webinar is being recorded. A copy of the webinar will be available on the STAC website that Yusuf is managing. So I'll open the floor right now for questions in the chat box. I also want to bring your attention again to the PDF at the bottom of the left-hand side if you want to download the slides from today's presentation. Link to the website. We'll definitely, I can go back to, oh, the STAC website. Okay, that's Yusuf, that's your domain. What is the link to the STAC website? You can type it in the chat box. And I think if you Google FHWA STAK, you'll be able to get to the STAC website. Yusuf, you are muted if you're trying to say something. Okay, you're not muted anymore. Maybe you are. Any other questions? Kiri is typing a question, so we'll see. You have to type the questions in the chat pod. You don't have any, you can actually just hear us. Okay, thank you, Charles. Charles provided the website for the STAC. I don't know if anybody is typing in the reduced data sets, but keep those in mind. You can also email them to us, and we'll make sure we'll share them with Federal Highway. I see several people typing, so let's see what we have in terms of questions. Thank you, Ed. Yusuf, I don't see any more questions. I'm gonna turn it back to you for closing words.
Okay, thanks Omar, and thanks Skylar for doing this webinar. I want to thank everyone for joining us today, and we hope that you have found this webinar informative and useful, and hope that you will join us for 4 more webinars in this series. Thanks.
All right. Thank you, everybody. Thank you, Yusuf. And we will be back on again in December. We will select a date and a time to try to minimize issues with other things that are going on. I know a lot of people have a busy webinar schedule, but we'll try to find a date that works for Federal Highway for us, and also that doesn't have a lot of webinars going on. So have a good afternoon, everybody. And again, thank you very much.